BANSAC, a dynamic Bayesian network for sample consensus. Outliers are one of the primary causes of poor performance in computer vision. Because of its robustness to outlier-contaminated data, RANSAC is the standard algorithm for robust estimation. Applications of RANSAC include camera localization, visual odometry, and 3D mapping, among others. RANSAC is an iterative algorithm that in each iteration randomly samples a minimal set, estimates a model hypothesis, and evaluates the model by comparison with the best model so far. Additionally, for efficiency, a stopping criterion can be added to avoid performing all iterations. Despite its robustness, RANSAC has its limitations. For instance, the random sampling step doesn't use any data priors that are commonly available or any geometric information, which can be useful to avoid selecting degenerate or outlier contaminated samples. Over the years, several authors have proposed variations to the RANSAC algorithm. For sampling specifically, PRO-SAC proposed to guide the sampling using matching scores, and progressive knapsack added to that some local geometric constraints. So, what we are trying to answer with this work is, will changing the scoring weights over iterations help in sampling and defining the stopping criterion? Our contributions in this work are a new adaptive sampling strategy that uses a dynamic Bayesian network to update data inlier scores, a new stopping criterion, and we show that our approach obtains state-of-the-art results in accuracy and efficiency in several applications using real-world datasets. We propose to model the inlier probability of each data point with the presented dynamic Bayesian network. The key idea is to use the successive classifications in inlier or outlier to update the probability. For instance, data classified as inlier in high consensus models should have an increase in its inlier probability, while outliers should have a decrease. We want to do inference about the probability of a point being inlier, knowing the states and classifications estimated per iteration. By assuming a first order of Markov, we can simplify the estimation by being independent of all but the previous state. Then, using the chain rule of probabilities and Bayes' theorem, we are able to update each data point probability using equation 1. In our paper we also test the second and third orders of the Markov assumption. For sampling, we want to use the updated probability values. For that, first, we convert the probabilities into weights in the range of 1 to 100 using an activation function. Then, we generate a weighted discrete distribution from those weights and sample a minimal set from it. We also want to use the updated probabilities to define a stopping criterion. The first step is to count how many outliers the current best model has before updating the probabilities. Then, after the update, we check how many data points have a probability below a certain threshold. We consider that points with probability below the threshold will not be sampled in the next iteration. Finally, if the number of outliers from the threshold is bigger than the number of outliers from the current model, we stop the estimation in the next iteration, because we most likely will only sample inliers. To validate BANSAC, we applied it to the problems of essential matrix, fundamental matrix, and homography estimation. We also tested two variants of our method. We refer to BANSAC when no prior scores are used and to p-BANSAC otherwise. For more details please refer to the paper. In our first experiment, we wanted to check only the performance of the sampling strategy of each method. For that, we removed the stopping criterion and varied the number of iterations given to the estimation. From these results, we see that for the same number of iterations our methods are the most accurate. This indicates that our sampling strategy is more efficient. For our second experiment, we vary the inlier ratio of the data by filtering matches based on their matching scores. The only differences between the methods are the sampling strategy and stopping criterion. We observe that our methods are the most accurate and efficient, even at lower inlier rates, meaning that our sampling strategy is successfully distinguishing inliers from outliers. Next, we show overall results across all sequences from the phototourism dataset for a fundamental matrix estimation problem. Overall, BANSAC is the most accurate and p-BANSAC is the most efficient. In this example, we show the evolution of the inlier probabilities. There are some clear outliers, and we can observe that those have a low inlier probability. For this next experiment, we ran an essential matrix estimation problem with all sequences from the phototourism dataset. Once again, BANSAC was the most accurate and p-BANSAC the most efficient. For our final experiment, we ran a homography estimation problem using the EVD and H-patches datasets. Results show that BANSAC and p-BANSAC are the most accurate methods. Here is an example of the evolution of probabilities over iterations in a homography estimation problem. To conclude the presentation, in this work we propose a new sampling strategy for RANSAC. Instead of random sampling, we sample data points based on their inlier probability. These probabilities are modeled by a dynamic Bayesian network and are updated every iteration based on the inlier or outlier classifications. Thank you for assisting the presentation. For any questions feel free to contact us.